The CANDU reactor is a Canadian-developed, pressurized heavy water reactor used for generating electric power. The acronym refers to its deuterium oxide moderator and its use of uranium fuel. CANDU reactors were first developed in the late 1950s and 1960s by a partnership between Atomic Energy of Canada Limited, the Hydroelectric Power Commission of Ontario, Canadian General Electric, and other companies. All power reactors built in Canada are of the CANDU type. The reactor is also marketed abroad and there are CANDU-type units operating in India, Pakistan, Argentina, South Korea, Romania, and China. In October 2011, the Canadian federal government licensed the CANDU design to CANDU Energy, which also acquired the former reactor development and marketing division of AECL at the time. Design, basic design and operation: fission reactions in the reactor core heat pressurized heavy water in a primary cooling loop. A heat exchanger, also known as a steam generator, transfers the heat to a light water secondary cooling loop, which powers a steam turbine with an electrical generator attached to it. The exhaust steam from the turbines is then condensed and returned as feed water to the steam generator, often using cooling water from a nearby source, such as a lake, river, or ocean. Newer CANDU plants, such as the Darlington Nuclear Generating Station near Toronto, Ontario, use a diffuser to spread the warm outlet water over a larger volume and limit the effects on the environment. A cooling tower can be used, but it reduces efficiency and increases costs considerably. Some of the unique features of the CANDU design are listed below. Use of natural uranium. Since CANDU uses heavy water as moderator and also as coolant, it has the luxury of maintaining a very high neutron economy. This means that the subsequent neutrons resulting from fission are used more effectively and there are fewer losses. This allows the use of natural uranium as fuel and saves the cost of enrichment. Pressure tube design. Pressurized water reactors and boiling water reactors are mostly pressure vessel type reactors. CANDU instead uses pressure tubes. Each pressure tube is inside the calandria tubes and there are normally 380 to 480 such tubes assembled in a reactor. This design enables the use of online refueling and many other unique features of CANDU. Refueling the reactor while it is in operation. Unlike PWRs and BWRs, CANDU reactors do not undergo batch refueling. Instead, two robotic machines hook up to the reactor faces and open the end caps of a pressure tube. One machine simply pushes in the new fuel, whereby the depleted fuel is pushed out and collected at the other end. In a light water reactor, the entire reactor core is a single large pressure vessel containing the light water, which acts as moderator and coolant, and the fuel arranged in a series of long bundles running the length of the core. At the time of CANDU's design, Canada lacked the heavy industry to cast and machine the pressure vessels. In CANDU, the pressure is contained in much smaller, easier to fabricate tubes. Each bundle is a cylinder assembled from alloy tubes containing ceramic pellets of fuel. In older designs, the assembly had 28 to 37.5-meter long fuel tubes with 12 such assemblies lying end-to-end in a pressure tube. The newer CANFLEX bundle has 43 tubes with 2 pellet sizes. It is about 10 centimeters in diameter, 0.5 meters long, and weighs about 20 kilograms and replaces the 37-tube bundle. To allow the neutrons to flow freely between the bundles, the tubes and bundles are made of neutron-transparent zircaloy. The zircaloy tubes are surrounded by a much larger low-pressure tank known as a calandria, which contains the majority of the moderator. To keep the hot coolant from boiling the moderator, a calandria tube surrounds each pressure tube, with insulating carbon dioxide gas in between. Slowing down neutrons releases energy, so a cooling system dissipates the heat. The moderator is actually a large heat sink that acts as an additional safety feature. The use of individual high-pressure fuel channels passing through the CANDU's low-pressure moderator calandria makes it easier to refuel. A pressure vessel reactor must be shut down, the pressure dropped, the lid removed, and a sizable fraction of the fuel, e.g., 1/3, replaced all at once. In CANDUs, individual channels can be refueled without taking the reactor offline, improving the capacity factor. One fueling machine inserts new fuel into one end of the channel while the other receives discharged fuel from the opposite end. One significant operational advantage of online refueling is that a failed or leaking fuel bundle can be removed from the core once it has been located, thus reducing the radiation fields in the primary systems. Purpose of using heavy water natural uranium is a mix of isotopes, mainly uranium-238, with 0.72% Wt fissile uranium-235. A reactor aims for a steady rate of fission over time, where the neutrons released by fission cause an equal number of fissions in other atoms. These neutrons are fairly energetic and don't readily react with the surrounding fissile material. They must have their energy moderated as much as possible, ideally to the same energy as the atoms themselves or lower. During moderation, it helps to separate the neutrons and uranium, since 238U has a large affinity for intermediate energy neutrons, but is only easily fissioned by the few energetic neutrons above approximately equals 1.5 to 2 MeV. Since most of the fuel is usually 238U, most reactor designs are based on thin fuel rods separated by moderator, allowing the neutrons to travel in the moderator before entering the fuel again. More neutrons are released than is needed to maintain the chain reaction. When uranium-238 absorbs just the excess, plutonium is created, which helps to make up for the depletion of uranium-235. Eventually, the buildup of fission products that are even more neutron-absorbing than 238U slows the reaction and calls for refueling. Light water makes an excellent moderator. The light hydrogen atoms are very close in mass to a neutron and can absorb a lot of energy in a single collision. However, light hydrogen is also fairly effective at absorbing neutrons, and there will be too few left over to react with the small amount of 235U in natural uranium, preventing criticality. In order to allow criticality, the fuel must be enriched, increasing the amount of 235U to an acceptable level. In light water reactors, the fuel is typically enriched between 2% and 5% 235U. Enrichment facilities are expensive to build and operate. They are also a proliferation concern, as they can be used to enrich the 235U much further, up to weapons-grade material. However, this can be remedied if the fuel is supplied and reprocessed by an internationally approved supplier. The main advantage of heavy water moderator over light water is reduced absorption of the neutrons that sustain the chain reaction, allowing a lower concentration of active atoms. Deuterium already has the extra neutron that light hydrogen would absorb, reducing the tendency to capture neutrons. However, deuterium is twice the mass of a single neutron. The mismatch means more collisions are needed to moderate the neutrons, requiring a larger thickness of moderator between the fuel rods. This increases the size of the reactor core and the leakage of neutrons. It is also the practical reason for the calandria design, otherwise a very large pressure vessel would be needed. The low 235U density in natural uranium also implies that less of the fuel will be consumed before the fission rate drops too low to sustain criticality. because the ratio of 235 U to fission products plus 238 U is lower. However, in CANDU most of the moderator is at lower temperatures than in other designs, reducing the spread of speeds and the overall speed of the moderator particles. This means most of the neutrons will end up at a lower energy and be more likely to cause fission. So CANDU not only burns natural uranium, but it does so more effectively as well. Overall, CANDU reactors use 30 to 40% less mined uranium than light water reactors per unit of electricity produced. This is a major advantage to the heavy water design. It not only requires less fuel, but as the fuel does not have to be enriched, it is much less expensive as well. A further unique feature of heavy water moderation is the greater stability of the chain reaction. This is due to the relatively low binding energy of the deuterium nucleus, leading to some energetic neutrons and especially gamma rays breaking the deuterium nuclei apart to produce extra neutrons. Both gammas produced directly by fission and by the decay of fission fragments have enough energy, and the half-lives of the fission fragments range from seconds to hours or even years. The slow response of these gamma-generated neutrons delays the response of the reactor and gives the operators extra time in case of an emergency. Since gamma rays travel for meters through water, an increased rate of chain reaction in one part of the reactor will produce a response from the rest of the reactor, allowing various negative feedbacks to stabilize the reaction. On the other hand, the fission neutrons are thoroughly slowed down before they reach another fuel rod, meaning that it takes neutrons a longer time to get from one part of the reactor to the other. Thus, if the chain reaction accelerates in one section of the reactor, the change will propagate itself only slowly to the rest of the core, giving time to respond in an emergency. The independence of the neutron's energies from the nuclear fuel used is what allows for such fuel flexibility in a CANDU reactor. Since every fuel bundle will experience the same environment and affect its neighbors in the same way, whether the fissile material is uranium-235, uranium-233 or plutonium. Canada developed the heavy water moderated design in the post-World War II era to explore nuclear energy while lacking access to enrichment facilities. War-era enrichment systems were extremely expensive to build and operate, whereas the heavy water solution allowed the use of natural uranium in the experimental ZEEP reactor. A much less expensive enrichment system was developed, but the United States classified work on the cheaper gas centrifuge process. The CANDU was therefore designed to use natural uranium. Safety features. The CANDU includes a number of active and passive safety features in its design. Some of these are a side effect of the physical layout of the system. CANDU designs have a positive void coefficient as well as a small power coefficient, normally considered bad in reactor design. This implies that steam generated in the coolant will increase the reaction rate, which in turn would generate more steam. This is one of the many reasons for the cooler massive moderator in the calandria, as even a serious steam incident in the core would not have a major impact on the overall moderation cycle. Only if the moderator itself starts to boil would there be any significant effect, and the large thermal mass ensures this will occur slowly. The deliberately sluggish response of the fission process in CANDU allows controllers more time to diagnose and deal with problems. The fuel channels can only maintain criticality if they are mechanically sound. If the temperature of the fuel bundles increases to the point where they are mechanically unstable, the horizontal layout means they will bend under gravity, shifting the layout of the bundles and reducing the efficiency of the the reactions, because the original fuel arrangement is optimum for a chain reaction and the natural uranium fuel has little excess reactivity. Any significant deformation will stop the interfuel pellet fission reaction. This will not stop heat production from fission product decay, which would continue to supply a considerable heat output. If this process further weakens the fuel bundles, they will eventually bend far enough to touch the calandria tube, allowing heat to be efficiently transferred into the moderator tank. The moderator vessel has a considerable thermal capability on its own, and is normally kept relatively cool. Heat generated by fission products would initially be at about 7% of full reactor power, which requires significant cooling. The CANDU designs have several emergency cooling systems, as well as having limited self-pumping capability through thermal means. Even in the event of a catastrophic accident and core meltdown, it is important to remember that the fuel is not critical in light water. This means that cooling the core with water from nearby sources will not add to the reactivity of the fuel mass. Normally the rate of fission is controlled by light water compartments called liquid zone controllers, which absorb excess neutrons, and by adjuster rods which can be raised or lowered in the core to control the neutron flux. These are used for normal operation, allowing the controllers to adjust reactivity across the fuel mass as different portions would normally burn at different rates depending on their position. The adjuster rods can also be used to slow or stop criticality, because these rods are inserted into the low-pressure calandria, not the high-pressure fuel tubes. They would not be ejected by steam, a design issue for many pressurized water reactors. There are two independent, fast-acting safety shutdown systems as well. Shut-off rods are held above the reactor by electromagnets and drop under gravity into the core to quickly end criticality. This system works even in the event of a complete power failure, as the electromagnets only hold the rods out of the reactor when power is available. A secondary system injects a high-pressure gadolinium nitrate neutron absorber solution into the calandria. Fuel cycles. A heavy water design can sustain a chain reaction with a lower concentration of fissile atoms than light water reactors, allowing it to use some alternative fuels, e.g., recovered uranium from used LWR fuel can be used. CANDU was designed for natural uranium with only 0.7% U-235, Saru with 0.9% U-235 is a rich fuel. This extracts a further 30 to 40% energy from the uranium. The DUPIC process under development can recycle it even without reprocessing. The fuel is sintered in air, then in hydrogen to break it into a powder, which is then formed into CANDU fuel pellets. CANDU can also breed fuel from the more abundant thorium. This is being investigated by India to take advantage of its natural thorium reserves. Even better than LWRs, CANDU can utilize a mix of uranium and plutonium oxides. The plutonium either from dismantled nuclear weapons or reprocessed reactor fuel. The mix of isotopes in reprocessed plutonium is not attractive for weapons, but can be used as fuel, while burning weapons-grade plutonium eliminates a proliferation hazard. If the aim is explicitly to burn plutonium or other actinides from spent fuel, then special inert matrix fuels are proposed to do this more efficiently than MOX. Since they contain no uranium, these fuels do not breed any extra plutonium. Economics. The neutron economy of heavy water moderation and precise control of online refueling allow CANDU to use a great range of fuels other than enriched uranium, e.g., natural uranium, reprocessed uranium, thorium, plutonium, and used LWR fuel. Given the expensive enrichment, this can make fuel much cheaper. There is, however, an initial investment into the tons of 99.75% pure heavy water to fill the core and heat transfer system. In the case of the Darlington plant, costs released as part of a Freedom of Information Act request put the overnight cost of the plant at $5.117 billion CAD. Total capital costs including interest were $14.319 billion CAD, with the heavy water accounting for $1.528 billion, or 11% of this. Since heavy water is less efficient at slowing neutrons, CANDU needs a larger moderator-to-fuel ratio and a larger core for the same power output. Although a calandria-based core is cheaper to build, its size increases the cost for standard features like the containment building. Generally, nuclear plant construction and operations are approximately equals 65% of overall lifetime cost. The CANDU costs are dominated by construction even more. Fueling CANDU is cheaper than other reactors, costing only approximately equals 10% of the total, so the overall price per kWh electricity is comparable. The next generation advanced CANDU reactor mitigates these disadvantages by having light water coolant and using a more compact core with less moderator. When first introduced, CANDUs offered much better capacity factor than LWRs of a similar generation. The light water designs spent, on average, about half the time being refueled or maintained. However, since the 1980s, dramatic improvements in LWR outage management have narrowed the gap, with several units achieving capacity factors tilde 90% and higher, with an overall fleet performance of 92% in 2010. The latest generation CANDU 6 reactors have an 88 to 90% CF, but overall performance is dominated by the older Canadian units with CFs on the order of 80%. Refurbished units have demonstrated poor performance to date on the order of 65%. Some CANDU plants suffered from cost overruns during construction, often from external factors such as government action. For instance, a number of imposed construction delays led to roughly a doubling of the cost of the Darlington nuclear generating station near Toronto, Ontario. Technical problems and redesigns added about another $1 billion to the resulting $14.4 billion price. In contrast, in 2002, two CANDU 6 reactors at Kashan in China were completed on schedule and on budget, an achievement attributed to tight control over scope and schedule. Nuclear non-proliferation. In terms of safeguards against nuclear weapons proliferation, CANDUs meet a similar level of international certification as other reactors. There is a common misconception that the plutonium for India's first nuclear detonation, Operation Smiling Buddha in 1974, was produced in a Cyrus design. In fact, it was produced in the safeguarded indigenously built PHWR reactor. In addition to its two PHWR reactors, India has some safeguarded pressurized heavy water reactors based on the CANDU design, and two safeguarded light water reactors supplied by the U.S. Plutonium has been extracted from the spent fuel from all of these reactors. However, India mainly relies on an Indian-designed and built-in military reactor called Dhruva. The design is believed to be derived from the Cyrus reactor, with the Dhruva being scaled up for more efficient plutonium production. It is this reactor which is thought to have produced the plutonium for India's more recent Operation Shakti nuclear tests. Although heavy water is relatively immune to neutron capture, a small amount of the deuterium turns into tritium in this way. Tritium plus deuterium mix undergoes undergoes nuclear fusion more easily than any other substance. Tritium can be used in both the fusion boost of a boosted fission weapon and the main fusion process of an H-bomb. However, in an H-bomb, it is usually created in situ by neutron irradiation of lithium-6. Tritium is extracted from some CANDU plants in Canada, mainly to improve safety in case of heavy water leakage. The gas is stockpiled and used in a variety of commercial products, notably powerless lighting systems and medical devices. In 1985, what was then Ontario Hydro sparked controversy in Ontario due to its plans to sell tritium to the U.S. The plan, by law, involved sales to non-military applications only, but some speculated that the exports could have freed American tritium for the U.S. nuclear weapons program. Future demands appear to outstrip production, in particular the demands of future generations of experimental fusion reactors like ITER. Currently between 1.5 and 2.1 kilograms of tritium are recovered yearly at the Darlington Separation Facility, of which a minor fraction is sold. The 1998 Operation Shakti test series in India included one bomb of about 45 knots yield that India has publicly claimed was a hydrogen bomb. An offhand comment in the Bark publication Heavy Water Properties, Production and Analysis appears to suggest that the tritium was extracted from the heavy water in the CANDU and PHWR reactors in commercial operation. Jane's Intelligence Review quotes the chairman of the Indian Atomic Energy Commission as admitting to the tritium extraction plant, but refusing to comment on its use. However, India is also capable of creating tritium more efficiently by irradiation of lithium-6 in reactors. Tritium emissions. Tritium is a radioactive form of hydrogen, with a half-life of 12.3 years. It is produced in small amounts in nature, by cosmic ray interactions in the upper atmosphere. Tritium is considered a weak radionuclide because of its low-energy radioactive emissions. The beta particles travel 6 mm in air and only penetrate skin up to 6 micrometers. The biological half-life of inhaled, ingested, or absorbed tritium is 10 to 12 days. Tritium is generated in the fuel of all reactors. However, CANDU reactors generate tritium also in their coolant and moderator. Due to neutron capture in heavy hydrogen, some of this tritium escapes into containment and is generally recovered. However, a small percentage escapes containment and is considered a routine radioactive emission. Responsible operation of a CANDU plant therefore includes monitoring tritium in the surrounding environment. In some CANDU reactors the tritium is periodically extracted. Typical emissions from CANDU plants in Canada are less than 1% of the national regulatory limit, which is based on International Commission on Radiological Protection guidelines. Tritium emissions from other CANDU plants are similarly low. In general, there is significant public controversy about radioactive emissions from nuclear power plants, and for CANDU plants one of the main concerns is tritium. In 2007, Greenpeace published a critique of tritium emissions from Canadian nuclear power plants by Dr. Ian Fairley. This report was criticized by Dr. Richard Osborne,